So we're into our second half of the morning. Uh, I think we're very lucky to have Leslie Sims with us. She's going to present on hypoxic fire prevention systems. We have a building in Oakville. We do have a building permit proposal coming in for this system. So I know I'm looking forward to your presentation, and I will let you introduce yourself.
Okay, then. Good morning, everybody. I want to say thank you for having me here today presenting. I've been involved in some of these hypoxic systems here in Canada. They are relatively new to Canada. We've had a system installation in London, Ontario for the Dr. Oetker pizza factory and the High Bay freezer warehouse, and I've been involved in a couple other projects in Canada. There is only, to my knowledge, only 2 or 3 operating systems that have been installed in Canada. There are some in the US, and our involvement really started because of our work. So I'll go back to a little bit about me here. We're building code consultants, fire safety consultants, fire protection engineers, and that's our involvement in the building industry with supporting fire and life safety in buildings led us to working on the Dr. Oetker facility and bringing forward the alternative solution to use the hypoxic system. And it was a substitute. It was to remove the sprinkler systems in the High Bay freezer warehouse. It wasn't novel to Dr. Oetker. They had already done this in their facilities in Europe and predominantly in Germany. And they wanted to bring this into, have it come with them to Canada when they built their first facility in Canada, at least in the first pizza, that investment on that. We've been in the game of fire prevention or fire building code consulting, fire protection engineering for 30 years. We're based in Mississauga, so there's a few familiar names through the participant list where we have worked with fire departments and building departments to demonstrate code compliance or to introduce alternative solutions. So I think that's probably more than enough about me. Steve, or sorry, Gary, what I can do here is probably just start. I've prepared a slideshow. I think it's easier to have the notes. We can talk about this as we go through. So I can bring that up.
Yeah, you should be able to share your screen, the button on the bottom, the green button.
The green button on the bottom. Sorry, I should have done this in advance. Share screen. Okay. Share, and let me just have this up. Okay, so what I think may work here is there is a lot of content to go through, but if there's questions that pop up, if you want to put them in the chat, I'll try to answer them as we go. Some of the questions may be leading in advance of where it may be coming up in a later slide. But I'll try to do my best to cover this. There's a lot of content in here. There's a lot to discuss. I'm sure there's lots of questions that come up from this. But I thought what I'd do is I'd start by describing what the systems are and how they work and sort of giving a background on that, because this the whole concept and how it works may be new to some of you. So I think it's worth going through that. And then we'll try to talk about some of the more practical questions that you may have, like system reliability, what happens if and when there's a fire, fire department response. So I'll try to do my best to respond to questions if I see them pop up on the chat as we go. Or Gary, or you feel free to interrupt and say, here's a good question.
We'll help you.
We'll watch.
Okay, great. So let me launch into it. So let's just start the term, because you'll hear these systems called many different names, but they are typically referred to as an oxygen reduction fire prevention system, or a hypoxic fire prevention system. It's synonymous. Hypoxic does mean a low oxygen environment. So what you'll see, there's a few other terms, there's a few trade names that are out there that you'll see being used, but essentially the concept is we are going to achieve fire prevention within the protected floor area. It's by maintaining a continuous hypoxic environment, which means that you've reduced the oxygen level in the protected floor area, and it's done by the introduction of nitrogen. So you bring in really oxygen poor, nitrogen rich air into the space. You put more oxygen or nitrogen into the space through the injection, and what it does is it alters the oxygen level within the space. It is referred to as a fire prevention system because it's an active system. It's ahead of a fire occurring. It's going to maintain an environment that doesn't sustain fire. Yeah, and I guess the slide pretty much has everything on there. That the oxygen's replaced with nitrogen. It's not a dangerous environment, not from the nitrogen being an inert gas, nor from reducing the oxygen to a point where it's not sustainable for people within the environment. So going back to basics of the principles of fire and how fire operates or how fire builds, we need 3 components. We need to have a fuel source, being the combustible elements within the space. We need to have the oxygen as part of the oxidation process and to bring on the fire, but you also need an ignition source. When you have those 3 in combination, we could have a fire occur. So what we see is we know that we cannot control the fuel in a space. In most cases, there are going to be combustible materials. And I'm leaning a little bit more towards warehouses when I'm talking about this, because we do see that these systems are being used in different environments as well, being IT rooms, museum archives. But the warehousing aspect, there's probably been more systems installed in warehouses than in the IT space or in the archive space. The ignition source is, again, also a variable that's very hard to control. So what we're doing here is removing the higher concentration of oxygen. So we typically, in ambient air, we have about 21% oxygen, about 78% nitrogen, and there's some other minor gases, argon, carbon dioxide, and other trace gases. But what we want to do is, it's the oxygen component in the air that we're trying to reduce. So we're going to, in an oxygen reduction fire prevention system, we're going to reduce the oxygen concentration to a point where we can't sustain fire. So essentially we're starving the fire. I mean, that's a term that many people are familiar with, and you see it, a closed box or somewhere where the air is no longer available to go to the fire will sputter out and not be sustained. In these types of systems, because we're, as opposed to removing the air after the fire starts, we're actually reducing the oxygen concentration prior to the fire starting. What they find is that we don't even get ignition, or if there is ignition, the fire really sputters and stays at a very, very limited size. So how an oxygen reduction fire protection system works, I feel like I'm repeating this a little bit, but the system's always on. This nitrogen injection is a perpetual. There's a plant that's always monitoring and injecting more nitrogen into the space. And what we do is, within this protected area, it's a continuous hold and a permanent environment with the oxygen concentration level being reduced from an ambient air level. And I'm going to get into how we determine what's the right level, about where do we know that we're at the right level. because that's really critical to say, you know, how much is enough, and where's that line between a place where fire could grow or too little oxygen that's not, that could eventually become non-sustainable. When you compare this, an active or a prevention system being always on, if you compare it to a sprinkler system, because that is really the comparison that we're coming to, um, a sprinkler system is passive in the sense that it's there and available and it reacts to the fire conditions. So it responds to the fire, it responds once there's sufficient heat. So it's that idea of fire prevention versus fire suppression. So this is what the change is. And I'll tell you, when I first started looking at these systems 5-6 years ago, it took me quite a time to kind of get my head turned away from sprinklers, because it's not a different sprinkler system. It's not like I'm replacing wet sprinklers with pre-action. It's not like I'm replacing a sprinkler system with a gas extinguishing system. You really have to get your head into, it's an active system, it's preventative, it's there and it's available, and it's that concept that I think took me probably longer to get my head around than a lot of the other features once within the system. It is similar to a gas and a flooding, gaseous flooding system like your Novec, your Energen, in that the way it manages the fire, it's by that the fire is eliminated, or we remove the oxygen component of the fire triangle, but we're not hitting it with that large drop or that large flood that the gas system has. So it's not kind of hitting it as hard, because we're not trying to catch up to try to bring the fire down. We're just not going to see a fire of that kind of size, if any. So what we're talking about as far as this reduced oxygen environment and how we get to whatever what the correct level is, the continuous oxygen reduced environment within the space. What we're trying, or what has to be established for the system to work, is that we have to have essentially a design concentration. So we have to say, this is the concentration of oxygen that we want to hold in this space. It will fluctuate slightly. That's going to happen as we have losses in the space with doors being open and the natural tendency for the space to want to revert to ambient. So we will see some fluctuation in the oxygen concentration, but it's going to bounce in a sort of a bandwidth of sort of a high and a low. But you want to set the design concentration of the system based on what an ignition threshold. And an ignition threshold, I put them in italics similar to our codes. It's a defined term that comes from the European standards, and the ignition threshold is established through testing, and it's related to the materials within the protected area. So it's different for different types of environments. Like an IT room would have a different concentration than, say, a warehouse with the packaging materials. In addition to so that ignition threshold is saying that's where we cross over between starving it and allowing a fire to grow. That's the threshold that we don't want to cross through. So we want to hold the oxygen concentration at a level below the ignition threshold. So we add a safety factor, which is per the standard, at least 0.75% of oxygen, plus an operating tolerance for the oxygen sensors, which has an accuracy rate of plus or minus 0.2%. So what you're seeing is the ignition threshold is typically, let me go back. The design concentration and the operating threshold is typically about 1% below the ignition threshold. There have been many tests done on different materials and different standards. It's also been demonstrated that the oxygen concentration it can be in it's the ignition threshold is inversely it's not proportional, but it's impacted, it's inverse to the temperature. So the colder the temperature in the space, the higher the oxygen level before ignition will occur. So that's a little bit intuitive. We know that when something's colder, it's harder for the fire to ignite, or it's going to take longer for a cold material to ignite than something that's already elevated. We see that with combustible liquids, flammable liquids. You've seen that with simple things like barbecues and heating up the space. The colder the air temperature, the longer it takes for the fire, or the temperature of the fire, to come up. Trying to think of what's next on here. So I want to go into the ignition threshold. So the ignition threshold is a defined term. The standard that's referenced there, the EN 16750, that is a European norm. And this European norm 16750, and I'll go through the standards that are available dealing with oxygen reduction fire prevention systems. I'll come to a slide later where I've got a list of them, but this European norm is specific to the oxygen reduction fire prevention systems, and it has to be through the use of nitrogen. So it's very specific. It's really been developed to address these systems. So within there, they do define that the ignition threshold as being the maximum oxygen concentration in a mixture, meaning a mixture of air, where between the combustible material in the air and the inert gas, where there's no ignition, and it's under established test conditions. And the test conditions are, I would say it's kind of like a small scale test. So the test conditions that they're running them on is basically a 10 by 10 by 10 meter container or space. And the material is placed in that space. The oxygen reduction level is brought down, and the combustible, or the material that you're trying to determine your ignition threshold for, it's subjected to an oxyacetylene, I think it is, torch, and it's a direct impingement on the surface of the material. And they measure for loss of material. They'll witness for fire spread, and there were several other materials in there. But it would be somewhat similar. The pass-fail is quite similar to the cone calorimeter test, where we're looking at a reduction in the material. So we're not seeing that we've lost any of the combustible materials through the test. So the ignition threshold is very specific to the materials in this space and the concentration of the gas. That standard does have an annex that has ignition thresholds for some typical materials, really based on packaging materials, some of the plastics that you see in packaging materials, the cellulose materials, the cardboards, the paper, the wrapping. They've also done testing on solvents. And then within that annex, they also have the testing protocol that they say for unfamiliar materials. So you can go and basically, this database will continue to be expanding about the different types of materials. The tests are typically done at ambient temperature at 20. So if you're looking to alter the, 20 degrees centigrade, if you were looking to alter the ignition threshold, knowing that you've got the cold temperature, you would have to do a test where you've got the temperature at a set temperature, you've got the combustible material, and you've also got the oxygen threshold. So it's a little, when you're testing for a new material, there's probably a few above the threshold, and then you start to run below. You have to run a minimum of 3 tests to determine the ignition threshold.
Leslie?
Yes.
Oh, sorry to jump in on you there. Thought you were done.
Nope.
Quick question from the question and answers relative to oxygen levels. The question is, if the oxygen level is relative to 2,700 meters above sea level and fire happens in those communities, how is this reliable fire prevention? So I'm assuming basically they're stating you're using the 2,700 meters above sea level as a reference point for those communities. So how can we use it is what I'm interpreting.
Yes, no, and so I think I know the answer to this. I think I looked this up several years ago, so I'm going to go off the top of my head here. The what was I going to say? So the 2,700 meters with that question, that's referring basically to the high altitude, and at that kind of high altitude, what we get into is a hypobaric condition where the oxygen level is actually at the 20%, what's in air, but that the elevation above sea level has created a different pressure, and you're under similar conditions as far as the oxygen saturation that you're seeing. It's similar to being in a hypoxic environment. I believe that these systems will still work at these higher elevations because the oxygen concentration in the air is the same at the higher elevation. It's just the pressure differential that creates a similar physiological environment for people. So I believe that the fire performance is similar with regard to like we don't see less fires at high altitude because we have less oxygen. They still will have fires in those environments. So the hypoxic fire prevention system will still work because it's differing the oxygen level by the introduction of the nitrogen versus so it's a normbaric hypoxic environment that you create within these systems or within these protected areas. Whereas the high elevation, it's a hypobaric. So you're kind of coming at it from two directions. I don't know the answer with respect to the impact on people because in a sense you're creating an oxygen reduction from two directions. But I believe from fire, the behavior is exactly the same.
Okay, thank you.
But again, this is going off the top of my head. Luckily, Oakville in particular, a lot of Canada, we're not working at those elevations. I don't even think we've got any communities more than maybe 1,000 meters above sea level. I'm not sure what the West is like in the Calgary area, but I don't think we're in it. Luckily in Canada, I don't think we're in an environment where we're going to have that conflict, but it's definitely worth making sure of prior to trying to install it in a higher elevation community.
Thank you.
Where was I saying? So there's questions that have been raised. This came up in our discussions with Oakville last week. NFPA, the foundation, has done some investigation into the research looking at these systems. There are some questions about the validity of the tests partly because they look for a homogeneous material. They're not doing large scale testing. I think those are valid concerns. But it can be countered by some of the historical data that we're starting to build up with these systems because some have been up and operational for over 15 years. I don't think it necessarily negates what we've got. It'd be like similar to saying, I just think that these systems are a little bit more in their infancy, where sprinklers, we've got 150 odd years of change and testing and data to help us. These are at an earlier stage, so I think we will learn more about the tests and the parameters and that kind of scaling. So I think what the NFPA, the foundation, the research foundation, the questions are going to push for greater development of the standards. This next slide is going to just illustrate the this idea of the ignition threshold versus the operating temperature and where the oxygen will flux within where it will fluctuate below your design concentration. So if you, X is essentially looking at over time, I'm not sure if this shows up my cursor as I'm talking here. I don't think so. But the X represents basically over time. The Y-axis represents the oxygen concentration. So the level, the line 2 or the dash essentially is your ignition threshold. So that's determined by testing. Oxygen concentrations above that level would sustain fire. Oxygen concentrations below that level do not sustain fire. And in this case, the markups on here were put in for the project installation in Manitoba. So these were the oxygen levels that concentration levels that we had to achieve within the warehouse that was installed in, where the system was installed in Manitoba. The first grid where the 0.75, so that first step down represents the safety factor that's mandated by the European norm. That is an absolute. The 0.2% represents the variance, the accuracy of the oxygen sensors in the space. Again, determined by, established that you have to put it in by the standard, but then you'd look at the manufacturer's data for their plus minus for their accuracy. So then that sets at line 3 what is our oxygen concentration, which is our design concentration. So that is where we want to be holding the environment at that level or lower. And so then what you see in the solid line that's moving up and down with the wave, that is the actual oxygen levels within the space. So you'll see that there'll be some bounce up and down that represents, you'd set the level, say at time 0, and then you're going to have you're going to push nitrogen into the space. As you build up more nitrogen, you're going to hit a lower oxygen level, and they're going to say, okay, that's enough for this space. So you hit your first low level set point. And it basically says, turn the nitrogen off for a little bit. We've got it, we're fine. And then over time, you'll see that the oxygen level starts to rise again through losses, through just infiltration in the building, opening, closing doors, just the tendency of the space to mix and return to natural ambient temperatures. So you hit a kind of a high point, and that's a demand point, and that's where the system calls for more nitrogen. You inject more nitrogen, and you'll cycle this way over the life of the building, with the nitrogen cycling up and down within a bandwidth that is determined to be below the design concentration level and above what we'd call basically an environment where we have too little oxygen, where we either don't want people entering the space, or it's just not efficient. Like we're just kind of pumping nitrogen in and there's no efficiency in there. So I'm going to come up with an illustration, just a schematic borrowed from Wagner, who's one of the suppliers of these systems. But our key components are, we need a nitrogen generator. What the nitrogen generator does is essentially it takes ambient air, and the nitrogen generator separates the oxygen component and the nitrogen component, discards the oxygen component, and filters the nitrogen so that the nitrogen can be the nitrogen-rich air at this point, and it'll be at 95 to 98% nitrogen. That's what's going to be put into the protected area. To get it into the protected area, there's distribution piping and a network for the injection into the space. It's very different than sprinklers. You don't need many injection points into the space because nitrogen it's very homogeneous and we get a blended environment. So you don't get pockets of just nitrogen and other pockets of oxygen. So it's very homogeneous, the mixture, even though the injection may only be at several points through the space. Absolutely key on this is that we need the oxygen sensors. They are located throughout the protected area and distributed at floor level, at a high level, and through the midpoints. Again, thinking of a warehouse, but even if it was another room, you would have a blend of them. The numbers and locations of the oxygen sensors has been established within within the norms and the standards in Europe. So the larger the space, the more sensors. It essentially, when we go back to the chart where we're talking about the oxygen level, that is a blended average of all the sensors. So a large space may have 14 or 15 sensors. So you will see that it's what we're coming back to as a blended average, which is nice. So if one sensor goes out of tolerance or goes into a failure mode, which would be noted by the controller, but the other sensors are still picking up the blended average, and they have a check with a alternative type of oxygen sensor that operates on a different mode, sort of the same photoelectric versus ionization and smoke detection. It operates in a different mode, so it sort of becomes the checkpoint for the calibration of the system overall. And all of this is controlled through a control unit, not a lot different than a pre-action alarm system. Well, actually a little bit different because there's a lot more bringing in this active data and then calling and pushing for nitrogen. But it's the control unit that is triggering for maintaining the environment, but it also triggers any alarms in a supervisory mode for warning and also in an alarm mode. So, and then that alarm mode, should that happen, we are able to put notifications out within the building, notifications through the building automation system, notifications to the fire alarm system. So in a schematic manner, this shows that we have the nitrogen production. It needs the compressors. The nitrogen generator works by taking air, and there's two ways that are predominant in the industry for producing nitrogen. One is through a membrane, a filter, so we have to push the air through a membrane, and the molecule sizes of oxygen and nitrogen are different. So the membrane has two sizes, one to screen the oxygen for discard and one for the nitrogen. There's also another way, which is to load a charcoal filter, and the charcoal filter holds the oxygen and the nitrogen is released. And then you take the pressure off of the membrane, or sorry, you release the nitrogen and then you take the pressure off the charcoal membrane, and that will release the oxygen. So the charcoal membranes are like, I'm going to say HEPA filtration, but it's not. But we've seen charcoal membranes for cleaning of air. They use it in nuclear facilities. They get loaded and then they reset themselves. So you just let them rest and they will reset. So that's how the nitrogen is made. The oxygen is just discarded. It just gets piped out and released back to the ambient air. So there's no how to say, there's no environmental impact from this. We're kind of just stripping the nitrogen out for the air, replacing the oxygen to the environment. The nitrogen rich air is placed into the green box, which is the protected area, and that's just piped through. It's just a standard 4-inch pipe that comes out, and it's just open-ended into the protected area. It does pass through a check valve so that it's pushed into that environment. So you have a solenoid valve that only allows the gas flow in one direction. The protected area is managed with the oxygen sensors. That feeds back into the control unit. That control unit then either calls for more or less nitrogen. If there's an upset condition, we have alarm devices both in the protected area. If we get too low of a level, to warn people to evacuate. If it's too high of a level, we'll have warnings on the outside of the protected areas saying do not enter. There's audibles, there's visual alarms. And then part and parcel with, in particular in warehouses, the European norm says once a warehouse gets over a certain size, we want to have an early detection system. So there's smoke detection within the space as well. So should there, for any reason, be a fire developing, which shouldn't happen because they've proven that this doesn't occur in the testing, but for whatever reason, we would have the early, they tend to use the air aspirating detectors to give you the very early smoke detection. And that would be sort of a conventional fire alarm. I don't want to go into too much more detail about the generation of the nitrogen. You're seeing this on the protection on dry pipe systems these days, where we're putting nitrogen within the system to reduce corrosion. Very similar idea. You get a nitrogen generator and it's always managing and pushing a little bit of nitrogen into the dry pipe system, and you're monitoring that environment. Again, another image borrowed from Wagner. This shows, so if we go back to this is just a schematic. This is kind of showing conceptually, you'd have a physical plant. It would be quite similar to a fire pump room where you have all your equipment. You'd have your compressors, you'd have your membranes, you'd have your control unit, and it's sitting in most warehouses we're dealing with our cold storage. So it's sitting in a room separate from the protected area. It was at ambient conditions, and it's not dissimilar to any mechanical service space. Again, a fire pump room or an HVAC area. The green pipe going across from the two, so you've got the compressors in the larger box, you've got the membrane filtration in the two cylinders. The green pipe in is the nitrogen into the space and the dispersion of that into the space. The blue lines within the box represent the smoke detection units. The small green boxes along the sides of the wall would be your oxygen sensors. So we have, they show an 8 and a 9, the 8 being the oxygen sensors that are blended, the 9 being the secondary checkpoint on the sensor. So to make sure the system's working, there's obviously lots of monitoring and supervision because it's quite, if you come back to here, there's not a lot to see. We've got maybe 2-3 pipes coming into the space. So when you're used to seeing sprinklers in a space and all the piping, you know, it's very visual to see where the protection is. This is an oxyreduct. There's no sense of where the gas is. You have to, you're reliant on the sensors. So you're always going to be continuously monitoring the oxygen concentration levels in the protected area. The sensors are, there's high, low, mid, there's the blend, there's the calibration of the sensors, both when they're installed and on an annual basis. So that sensor is pulling back or these sensors are pulling back information, saying more nitrogen, less nitrogen, giving warnings to people outside the space, inside the space, about if there's variances beyond the normal operating threshold. There can be supervision through the fire alarm system for what we'd say are abnormal, like the extreme conditions. The smoke detectors, there's also, you can supervise it through the building automation system. A lot of these buildings, warehouses have automated storage retrieval systems. So they're going to have a form of building automation system, basically a control room watching the conveyors, the in and out, and you can tie in your oxygen reduction fire prevention system. So all the building operators are aware of any conditions. They don't have to go into the plant area to get an alarm from the panel. And then we have smoke detectors in the protected area. So that's in addition and independent of the oxygen reduction fire prevention system. So that's just the smoke detectors, and that would feed right into the building fire alarm system or into a fire alarm panel. Reliability of the system. You have redundancy at the compressors. They cycle. There's on and on off. So, but each compressor is designed that it can take 100% of the load to maintain the environment. And this is all calculated. Sorry, I'm going to go back. This is all calculated by the supplier. They calculate. They may run the tests, or they'll have the data for setting your ignition threshold and your design concentration. They will size the equipment of the number of compressors, the number of nitrogen generators to be able to maintain that environment in the space. They factor in the number of openings into the space, the temperature, the conditions of the environment, prevailing winds. These will all be factors that contribute to losses. So they make sure that there's enough capacity within the generators to be able to maintain that. But then they will have sufficient compressors so that you only have to run one at any given time, but they will cycle them for ensuring that at least in the Wagner systems, they cycle them to ensure that they get one equal wear, but they're both operational. The compressors themselves they're industrial, they're standard units, so they're interchangeable. So there's not a lot of downtime should something happen with one of the compressors. It's not like there's a long lead time. The nitrogen generators themselves, there's not a lot of components within the generator because it's a membrane where you're passing through or you're loading and discharging. Most of the components upstream and downstream are valves, solenoid controlled valves, check valves to control the flow of the compressed air into the nitrogen generator and then the release of the oxygen and the nitrogen. Another factor on the system reliability, unlike sprinklers and unlike a gas suppression system, which kind of, there's a hard on, there's a release of a valve, there's a bang and a discharge, and we've got this, the fire protection system operational. These systems, the oxygen reduction systems, it takes time to get the environment set. So you've got a ramp up time, and in a large warehouse that can take 2 or 3 days to condition the space and get the nitrogen levels at that. But you'll also find that the reverse is true, that should the system go down, a power failure, whatever reason, the return of the oxygen levels is also gradual. So the full loss of the system in a tight warehouse, a cold storage warehouse, could take 2 to 3 days to return to an ambient level. You do have the system reliability. You've got multiple oxygen sensors. It is a blended average, but a failure of one does not create a failure of all of them. So they all pull in independently, but the blended average is drawn at the controller. So it's not like a linear or a system where it's I'm trying to think of the right term. They're all in parallel. They're not one after the other in a line. We also have a lot of alarms. You can have that set at a high and a low level. There's a warning level, and then there's another alarm at the other mode. And because the system's always on, we know it's there and working. So it's always being monitored. You're always getting feedback from the system. Again, a little different from a sprinkler system, which technically is always on because we've got water in the system. but sometimes you're not always monitoring it to the same extent, and you can have a condition that inhibits the operation of the sprinkler system, but it depends on whether somebody's responded, well, in any situation, whether somebody's responded to the supervisory alarms or the trouble alarms. But in this case, because it's always on and feeding information back to the operators, they're likely to see an upset condition versus somebody who's ignored or overridden an alarm. But there's no promises when people want to ignore alarms on fire protection systems. It can happen, and we've all heard stories about that.
Leslie, could I ask a
Yes.
question here?
Yes.
So you mentioned about, operations that have conveyors. So if there's a conveyor system installed and it goes from the oxygen reduction side to ambient oxygen, does your safety factor or your tolerances have to be adjusted for those type of openings?
Yeah, absolutely. So any type of opening, a man door, a material handling door, whether it be a smaller opening for a conveyor like sized at, or for a forklift with a load, those will all be factored in. And you'll see in the calculation that they do talk about number of openings within the space, and they do look at the insulation of the space. So now the conveyor openings, I'm going to get a little ahead of myself. I think that these systems are just perfect for high bay freezer warehouses that have automated systems, automated storage and retrieval systems. There's a lot of features within those within a high bay freezer warehouse that are compatible and working in the same direction as the oxygen reduction system. And that is that the environment is very tight. It's very controlled, that the operator is not going to allow doors to be open for extended periods because they're going to lose their temperature control. That's going to cost them money. It could cost them food products. So there's a lot of things that sort of the operator is going to do to protect their business, that also make sure that these oxygen reduction fire prevention systems are the features that we want to have in place for that to work. Any other questions?
Looks like we're good so far.
Okay, I'm going to keep going then. I should get a little quick time check here. So we're moving into it. So
45 minutes roughly.
okay, let me see. I'm going to try to, I've got a blank. I don't know what's happened on this. Sorry, next one coming. Design standards. So we don't have anything obviously in Canada yet, nor would Canada develop something like this. I expect that NFPA would be the leader within North America for it. But there are European norms and British standards that have been established for these systems. And I make a comparison to like an alternative solution, which sometimes rolls into BMECs, which then get put into standards. These systems were developed in Europe, so you'll see a prevalence of them in Europe. They have I think the starting document was the VDS 3257, because it was the Germans that Wagner's a German company, and they are the early developer of these systems. So they developed a guideline for the inerting and oxygen reduction systems. It's a combination of a standard and like a ULC listing requirement. So the VDS certification covers components. It covers that testing criteria to set the ignition thresholds, and it gives you the installation design criteria for number of sensors, concentration levels, safety levels. It also requires certified installers and sign off and commissioning. So it's very comprehensive. A little different than, say, the NFPA 13 standard, because it does have some of the testing criteria within that at the beginning, or not at the beginning of the standard, but included in the standard. The European norm 16750 is quite similar to the VDS guideline, but it's now a European norm, so it's applicable throughout the EU and any countries that have adopted the European norms. The PAS 95 is a British standard, again, similar in content, but developed by the BSI, which I believe is British Standards Institute in the United Kingdom. There was a standard, a Swiss norm for the systems in Switzerland, and CEN TC 191, which is fixed firefighting, which encompasses many systems, indicated they were going to be adopting or adding this. I think it would essentially be a chapter. And I mentioned to Gary last week that, and I haven't done the digging, I don't think it has been adopted yet. I don't think they've brought that into the standard. So where do we come when we come into Canada? How do we deal with this? Or how do we say, how do we install these systems? The only way to look at them is through the alternative solution protocol. And it can be a substitute for automatic sprinkler protection. They come to the same goals and objectives, which is to basically to limit fire spread and growth so that we don't have damage to the buildings and we don't have injury to personnel. And we talk about the objectives, and sorry, this slide is blank and I don't know why. So my apologies, but within the alternative solution, we do have both in the fire code and the building code, the pathway to allow us to come to alternative designs and to alternative systems. So really what we have to do under the alternative solution is to demonstrate that we're going to achieve a similar performance as that we would get from sprinklers. Now, it's not to say it's going to be the same performance because they come at it from two different angles, but the ultimate goal is to limit fire spread and fire growth so that we don't, from the point of origin. So it's not that we're eliminating it. It's not, you know, a fire protection or a sprinkler system says it is all about control and doesn't guarantee suppression. The hypoxic system will also limit any fire growth, or they're actually saying that they won't see fire growth. So historically, what they've seen in Europe is that they haven't had any reported incidents of fire, or if they've had a failure, it's been very small and contained. And I'm sorry, I don't have a good history and log on that, and that's something that I need to dive into. So everything I've been told is very anecdotal. I'm not sure there is a lot of data available at this point. So my apologies. I don't know why that slide comes up blank. I don't know if it's got an animation to it or not. So sorry, not there. So
yeah,
questions?
not a problem. Leslie, there's a couple
Yes.
of questions.
Sure.
First one, I'll just read it the way it was typed. Has there been any discussion or consideration of the type and construction of the rooms these systems are installed in? For example, the number and size of openings permitted, construction materials used, other systems, HVAC within the room. Just wondering if this system would impose restrictions of any kind on the room or area that it is being installed in.
So the system itself, like the standards, the European standards, they don't drive or demand any construction that would be different from what you would be doing in the building normally. You know, like, so it's not going to say, there's no restriction saying, oh, it can't be in a building that's combustible construction versus non-combustible. So that answers one part. The number and size of openings. So what happens is there's no restriction on the number of openings, but the more openings you have, the more places where ambient air will come in. And it just means that you're having to generate more nitrogen. So it's this idea of how easy is it to hold that environment versus leakage. So it's not really that you restrict it, but it is originally designed. So if there was a change once a building's up and established, and then you added another conveyor line or more openings, that would definitely impact the performance of the system. And it would have to go back into that design and saying, did we design enough capacity? Or what you're going to do is you're just going to cycle more. Like you're just going to say, instead of the nitrogen system turning on every minute, it's going to turn on every 30 seconds. So you're calling for the nitrogen more often. The HVAC systems, again, is a factor that goes in on the design side. It's factored in about the amount of fresh air that's introduced into the room, or what the exhaust rates are. So again, another reason why I think the freezer warehouses are beneficial or are compatible with this is that you're not changing the air a lot in these spaces. Like you get it conditioned, you get it cold, you don't want to introduce moisture. So the HVAC controls are very strict in these rooms. So on one answer is like, no, it doesn't impose restrictions, but you definitely have to consider it, because you have to understand, just like a gas extinguishing system, you have to know how many openings there are, because you have to factor that into your leakage.
Okay. Yeah.
Second question, I can answer that when I see it up on the screen.
Okay.
The BMEC, quite correct. The BMEC is probably the next step for these systems coming in. In particular, I think for warehouses, that they are being used in IT rooms. They are being used in archive storage or high value collection areas where they'll have a hypoxic environment. I do think the BMEC is a future step for this. We've seen this with other innovative systems that eventually we either go through a CCMC if it's a materials, or the BMEC. Last question. Give me a second, because I was just going to go into that about the health and safety. So let's see how we do on the next slide, and then I'll come back to that question. Okay, so worker health and safety. So these environments, hypoxic, are an oxygen reduced environment. There is guidelines in the VDS, the European norms, and the PAS for health and safety that talk about exposure and acceptable time limits for people to be in there. Going back a step, the environments that they're holding at the 14, 15%, even 16%, they're not hazardous to people's health. These are environments, like we were talking about the 2,700 meters. It's comparable to living at a high altitude environment. It's comparable to traveling in a plane. But there you're into a lower oxygen level from high altitude, that idea of thin air. But it's actually, you see some people benefit with endurance from that. It's been used for athlete training, working in hypoxic environments. So there isn't a, it's been demonstrated through studies outside, not just related to the oxygen prevention systems, that these low oxygen or high altitude environments are not hazardous to health. But so in the VDS and in the European norms and the British standards, they do have limits for different thresholds. So if the environment's between 21, which is ambient air, to 17, it's training and instructions, just advising what the environment is. Between 17 to 15%, what they require is that there's a general health screening for employees prior to, like, and I can't remember if it's on an annual basis or prior to working in these environments. They also say that you're limited to 4 hours within the space, and then you need a 30-minute break in an ambient condition. There's signage at the entry points to say you're entering into a hypoxic environment. And we have alarms at if the oxygen level goes below 17%, that there would be alarms that trigger to warn people that that the system has gone below the prescribed level of 17%. So, but then when we get into, so this is how they manage it in Europe. But when we get into an installation in Ontario or in Canada or within North America, we're dealing with the labor and workplace safety, and Ontario Labor will treat these as confined spaces because we're at an oxygen, I think they say at below 19%. If you're entering a space at below 19%, the breathing apparatus is required. So and this is something that both Dr. Oetker and the installation in Manitoba, they realized, one, that they don't have people entering the space very often because it was all automated storage and retrieval. And at the times that they would go in, they would they'd be trained and wear the breathing apparatus. They realized that that was worthwhile to have that on, and that they would talk to the Ministry of Labor and they would try to get a site-specific waiver for that, because the 19% was really geared around like the tanks and the sewer entry, where we could have where you had people being overcome by the lack of oxygen or by the other fumes. So they've got a wide capture on it, not anticipating something like this, but it hasn't been something that's been tackled yet as far as dealing with exposure and is it a safe environment or not. But the studies and that have been both commissioned by the providers of these systems, as well as what's out in the general cybersphere, show that a lot of hyperbaric and low oxygen environments are not harmful for exposure. Do all materials in the environment go through the ignition limit testing? I'm going to see if I can answer that. So for the ignition limit testing, it's the materials that you're expecting within the space. So in the warehouse, it would be the packaging materials, the commodities that are being stored. Typically what they would do is just get a sample of the materials. Dr. Oetker, it was relatively easy for them, and they had this done earlier from their first installations in Germany. They actually took the pizzas, the packaging, the skids, and that was what they did the fire test on. We don't have to worry about building materials. That's really established, like the construction materials. That's already established by the building code. But we do also anticipate any electrical fire sources with any of the robots or the conveyors that are in that space. So I don't know if we could say we do 100 tests for 100% of everything that could be in this space, but I think it's fairly representative of the combustible materials that would be in the space. I've already mentioned that I think that these systems are just ideal for cold storage warehouses or freezer warehouses. The configuration of the space. So what we're seeing now is that there's one on Mississauga up on the highway up at the northwest corner. You'll see these tall buildings, 30, 40 meters high. And they're just cold storage. They're running at temperatures -20 to -25 degrees C. They tend to have very dense storage, especially when you've got the automated storage and retrieval. And they're skinned and insulated, so they're very tight buildings. So it's just place the materials, hold them in this basically oversized cold storage freezer, pull them out when we need them to be distributed. And so again, a very tight box, and some of these are a box within a box, and some of these are rack supported structures that are then insulated and skinned with the insulating material. So the nature of holding that cold temperature, the limited entry into the space because it's on On the automated retrieval, the nature of being at minus 20, 25, nobody's going to stay in there for extended periods at any point in time. They're all very complementary to the oxygen reduction and the oxygen reduction system. We know the challenges of sprinklers in cold storage. You know, freezing temperatures water is not going to work well together. Accidental discharge, whether it's bumped by material handling, failure of the sprinkler mode, even a trip of the dry pipe valve. We get water in that pipes if it's either discharged from the sprinkler or it's even contained in the pipes. We tend to get a lot of ice loading on the materials or on the or within the pipe. We can get ice dams from not having a good compressor. So if we get moist air in there, so getting plug systems, you know, you may not even know where a plug is on a freezer system unless it's bad enough that you blow the pipes apart and you lose the air pressure. To get that restored is so much work. You have to unload the freezer, you have to bring it up to temperature, or you have to heat the pipes. So restoration of sprinkler systems, we've heard of systems where they have been frozen up for years without being addressed. So basically, I think a faulty operation could lead to an unprotected space. We've challenges just the size of the systems. We need a lot more intervention because of the capacity limits. The high ceiling heights, we also have challenges that we haven't had fire protection systems tested or sprinklers listed up to these heights. So we end up with more in-racks, or we tend to be leading towards alternative solutions anyways. The added bonus with any fire prevention system or any form of fire prevention, even early warning smoke detection, is that if you can get to that or eliminate a fire or prevent it from growing, you're going to limit the smoke damage. By the time a sprinkler system operates, there's going to be smoke damage, and the commodities are basically slated for destruction. There's no recovery at that. So in these large warehouses, you know, I don't even know what the cubic square footage is, but that's a lot of product. So this is why a lot of owners are leaning towards the oxygen reduction. For them, it's not only the building protection, but it's their inventory. Talk a little bit about, there's about 700 systems installed in more than 20 countries. That's probably outdated. There's probably more than that. They are predominantly in Europe. When they talk about systems, it's not necessarily buildings. I believe Wagner will call a system their compressor and one set of compressors and membranes as one system, just like we would call one dry pipe valve a system. But still, there's quite a few of them in operation. The majority are within the 10 countries that have this, the countrywide, that are covered by the European norm. And some of these have been operational for more than 15 years. The installations that I know of in Canada and the US, Dr. Oetker in London, which I did a lot of work on between getting the approvals for it to be installed, plus the follow-up engineering, supervising the design document or review of the design documents and the installation and commissioning. There's an installation for Simplot in the Manitoba. There was one approved for in Sackville, New Brunswick. I don't know if they actually did install the system or not, but they did get the approvals to go forward with that. In the US, again, a couple of the cold storage facilities. There's a couple in the West Coast in the Washington area that are there, but I think there's more than that in the US. I don't have a good list of what's in the US. They are used in cold storage facilities, data centers, high value archives. So what I'm going to do is, I'm nearing the end. I've got a few photos if we want to show of one of the installed systems. Do you want me to run through that, or we can open for questions?
I think showing some of the photos would be beneficial. While you're going there, I do have a question. You mentioned depending on the size, a fire alarm system could be required under one of those standards. Is the size based on the area or the volume of the room?
Volume.
Volume.
Yeah, the volume of the space dictates whether or not smoke detection is required in the protected area. Now, some buildings may fall outside of the requirement for a fire alarm system because they either don't have enough people. Like these are all warehouses are F2s. They don't have large numbers of people in them. So far, the systems that we've worked with, the building already had a fire alarm system or they were planning to put one in. So it worked in conjunction with that. Sorry if that, I'm not sure if that answers the question, but I think we would just say, put a fire alarm system in, like for what we're asking on these installations. It gives an extra level of assurance that should something happen, there's going to be kind of a conventional way of being advised of that and having early warning to investigate or to notify fire department. I may have some slides out of order. So typical arrangement of a high bay freezer warehouse, you have a large warehouse. In the central, you'll have a dock area for the automated retrieval system to load and unload and to transfer to trucks. You'll have a utility space. This is the one we're looking at in Oakville. It's going to be 120 by 60 long by wide, but 40 meters high. So we're up into the 10 million cubic feet of storage by the time you put all these kind of dimensions together. It will be a rack supported structure, minus 25. It's all variety of frozen food products because they are a third-party logistics company. So they are handling other people's products, but it will have the full automated storage retrieval system so no people not working within that space. So really what we have is a giant cold storage or freezer box. So what we're trying to do is protect within there because, you know, we're not saying it's a piece of equipment. We did try that with London and it didn't go because there's people going to be coming in and out, but there's comparisons to come into that. This is a drawing from one of the plants and one of the facilities. So you'll have the compressors lined up and then you'll see the two circles are the nitrogen generator or nitrogen filters. You have two because, well, one's doing the separation of the nitrogen, like is loaded with the pressure. The other one is on returning to ambient pressure and releasing the oxygen. So they cycle on and off these two generators. And in this case, we had two systems. So and each system technically could feed the building sufficiently, but it would be running a lot. So there was another level of redundancy. The green pipes coming out show that the nitrogen coming into the plant area. So this is, well, it's a screenshot of an architectural, but you can see by the different colors on the layers. But these are the Wagner, the oxyreduct. These are the membrane. The membranes they use, it's called VPSA, vapor pressure swing absorption or something like that. So this is the idea that it's all done under pressure and through the pressure it loads into the, it's adsorption, so it's loaded into the charcoal membrane. The compressors over here on the left-hand side, it can be a bit of a noisy plant at times when the compressors are running. Just another shot of the space. There was probably a comment about redundancy. There is emergency power provided to the controllers and to the sensors. So the brains and the intelligence and the monitoring is under emergency power. The physical plant, the mechanical components don't require emergency power because we've got the ability to basically shut the system down and we have a good hold time. A photo of the compressors. another shot just looking at the piping. The piping's quite discreet. We have the solenoid here for the separation for altering between one, sorry, this is actually, I can't remember what that is, sorry. We have a check valve down on the wall further down, feeding into the pipe that's leading, that goes into the plant. And I realize you guys can't see where my cursor is, so that doesn't help. You can see the two check valves. That's just to alter between one system or the other, not to have any backflow. The sensors, the Wagner material comes, it is certified and listed ULC for installation in Canada. But the one on the left is the oxygen sensor. The one on the right is the air aspirating smoke detector. I said when I first went into the plant, I was expecting red because I've seen so many fire protection devices in red, and I wasn't expecting the white. I'm searching around for them, not recognizing what the boxes on the walls were until later. On the control panel, they do have a display screen with controls, operator controls. Tells you what, at this point, you'll see, like it says the oxygen level. We didn't have any air or we weren't running the system at the time. This was before we brought the conditioned space. So you'll see the sensors reading the ambient air at 20.2. It says that the nitrogen is switched off. So that's at the operator controls back at the control panel. It's also monitored in the Wagner's case. It's monitored through their control room, but the operators in the building are familiar with it, will be trained and be familiar with how to use that. Warning signs at the entrance. So we simulated a low oxygen at 12.6, and there's a warning saying no entrance. And there's also, I believe there's an audible device tied with this as well. And the same kind of warning within the space, within the protected area. These warning lights are at the accessible areas, or they can be placed wherever we need. And that's really the tail end of the presentation that I have here. So what I'll do is just come up and open this up for questions.
Okay, I'm not seeing any right now. Oh,
They're going to come. You know what we didn't talk about was, fire response or emergency response. And I can speak to that if there aren't questions, but.
I think Steve might have a question. I don't know if he can still talk.
Yeah, no, can you hear me?
Yeah.
Okay, great. That was great. Thank you, Leslie. That was very informative. Yeah, I was aware of some of the, I waited with bated breath for the NFPA. I believe it's September this year. They're anticipating some kind of report on it. It smells similar to the NFPA 770, absence of the hybrid with water in there. You have the nitrogen and the hypoxic environment and so forth. I guess I have two questions. One, and I may reach out to you after if that's okay, because I probably have a million questions. But the one, and I'll tie into my presentation before, I understand, the lack of, we'll say, a North American standard and so forth. But your experience now that these are going in, what is the applicable maintenance standard that could be applied? Like it gets put in installation to standard manufacturer and all that. So what happens now year 2, 3, 4, 5 down the road? Effectively, how are these being looked at or maintained?
So maintenance, maintenance obviously is going to fall on the owner. If you've so in the European norms, they do have a requirement for ongoing maintenance, and that by qualified and competent people to be carried out. And they do have a schedule for the maintenance, but it's typically the oxygen sensors need to be calibrated in accordance with manufacturer's instructions. There'd be for the compressors, the maintenance. And I'm not sure what they have on the panel, to tell you the truth, but so there is a requirement for ongoing maintenance, just like any fire protection system, prevention system, any building system. Enforcement of that, how we managed it both in London as well as in Manitoba, is through the documented fire safety plan for the building. Both buildings were large enough that they have a fire safety plan. We bring the maintenance requirements into the fire safety plan, so that's there and available. And then the maintenance of the records. As far as these systems, the supplier of the equipment, Wagner, does do maintenance contracts where they are coming and doing annual checks, and they are monitoring the system. But I think it's just like any fire protection system. It's going to fall on the owner to ensure that they are keeping that operating. I think that's also another reason that it's good to have. Well, I guess it doesn't quite work. I was going to say, if you're monitoring your fire prevention system through the fire alarm panel, you would get trouble alarms and supervisory alarms for upset conditions. That doesn't necessarily tell the fire department. So I think it's that relationship between the building operator and the fire department to demonstrate that they're complying. But that's essentially how we've done any specialized fire prevention system. We've documented it in the fire safety plan, so we've got a place to track it.
Awesome. Thank you. Thank you. Actually, curiosity, who are the contractors that did that work in Winnipeg and in London?
To install it?
Yeah.
You can just use, it kind of falls in a funny place. You don't need to use a fire protection contractor because it's not like you're installing a sprinkler system. So the plant can be installed by someone who's familiar with installing mechanical equipment. The electronics are installed by an electrician, but the commissioning and the verification is done by the equipment supplier. So the tie-in and the harmony is done by, in the Oxy Redux systems, was done by Wagner.
Okay, thank you.
Just before we got into a couple of questions there, you had mentioned about fire department's response to these buildings. Is there anything in the standard regarding that, or is it just notification, letting people know not to expect a sprinkler system?
No, so as far as sort of notifications and things, or fire department, really they have instruction and training of personnel within the building. There isn't anything in the standard that says you have to engage the fire department. Again, through the alternative solutions, that kind of stuff was rolled in because we did talk about ongoing maintenance within there. We did speak to, the fire department was involved in review of all these alternative solutions. The building departments didn't do it in isolation without the fire prevention officers looking at it. And I think they also consulted with the suppression side and the response. So there was knowledge of what was happening, but there isn't anything in the standard that says you have to have the authorities involved.
Okay. Now, are there any vestibules in the, I'll say in the warehouse, so that you open up the one door and you're not starting
Yeah, typically what they'll do is a lot of these conveyor systems will be vestibuled anyways, to be a bit of a thermal bridge and a protection of the cold environment. So again, this is why I think it works nicely, how they're trying to protect the cold environment. It also works for the oxygen reduction. There will be some bleed out of the oxygen reduced air. So what they do is they do put sensors outside of the space in the vicinity of the doorways. So it's not that that you're unaware of what's happening there. But yes, there will be, depending on how long the opening's open for. But typically it's like a man trap, right? Like one closes before the other one goes through. So it's a staggered, and they can just be the rapid doors up, down, like they move pretty quickly, but the idea that you'd never have a clear opening between the two.
All right. Now, and I also see in the chat, there's a question about, is there any limitations on the size of the systems?
They don't, no, there's no real limitations on the size of the systems, but you will have to buy more systems or install more systems to protect a larger environment. So, and I can't remember the volume of the space in either Dr. Oakville or Manitoba. I should have it, but I think it would be comparable to what we're talking about in Oakville. In Manitoba, to get it to work, they ended up with 3 systems, like 3 sets of compressors and the double membrane in order to get the right volume of nitrogen to hold in that area. I think at the London one, I think there's 2. I think there's only 2 in the London one. So those photographs for the London, and I can't remember the volume of that space. So as the building scales up, the oxygen reduction systems scale up. Quite honestly, really what you get into is more limitations on the build and the construction. Like these buildings tend to be tall, narrow. So, you know, we have to watch prevailing winds. And then we have to also start thinking about egress and exiting and things like that. So I think what you get is that you get multiple freezer boxes and with multiple systems in each of the freezer boxes.
Okay. Now, is it also practical to install at data centers these type of systems, especially the question is actually if more than 50,000 square feet?
Okay, probably on the same kind of answer as the other one. It's all scalable. This is what I've been told mainly by Wagner, is that it's all scalable. I haven't looked at the data centers to the same extent because we just haven't been involved in that. I know that they work, it seems, in the sense that I think they end up being at about 17% oxygen concentration levels, so that allows personnel to work in that. I don't know the sizes that they've actually got installed, but I've never heard of a limitation because of that ability. Yeah, you just keep building a bigger plant, you build a bigger building, you build a bigger plant, you buy more systems.
One question just popped up in the Q&A. Can you speak to the suppression side of this, responding to a call?
Yeah, absolutely. To the extent that I am, like, there's no way I'm on the suppression side, knowledgeable about how a fire department would respond to any fire or set up for this. But I think as far as a response to a fire, in particular, a couple of things, and I started with this, Gary, I'll say, the chances of you having to respond to a fire are minimal because we're in a fire prevention mode. So I think, and you have a lot of warnings of early intervention, in particular with the smoke alarm, smoke detection in the space. But should the fire department respond, as far as firefighting, I think in this case, or any case, like if it was a sprinkler system that wasn't operating properly, it's all going to be on manual suppression. So it's going to be determining how you enter the space, how far you want to penetrate in, and it's going to be on hose lines. So what we do not have is, like, we don't have a backup, say like a dry header and a dry sprinkler system where you could pump fire into, like, into open sprinklers. I suspect that fire suppression teams are going to be leery about entering a rack supported building, regardless of the type of fire protection or fire prevention system within there, because I don't know if they'd be comfortable with the height of the storage and knowing that structurally that racking, which is holding the load of the commodities, is also holding up the skin of the building. So I suspect that you end up with a lot of exterior firefighting. And so what we did in London is we made sure that there was access around the perimeter and that there was good hydrant coverage. So we added private hydrants in the vicinity so that it was easier to establish hose lines near the freezer.
Right.
Yeah, like, and if you Google like the Dr. Oetker facility in London, it's a long building. It's incredibly long, the production side, and then the freezer warehouse. And I believe it's all designed as one building that isn't separate firewalls or anything. So technically, you could only have your fire department response at the front side of the building into the office area, because that's, as a sprinkler building, that would be the only place that you'd want to come or need to come into. So we made sure that there was access, fire route access to the backside, which is again relatively easy because we've got truck vehicles or to the loading and unloading area, and we had the hydrants in that area.
Right. Yeah. Okay. I'm not seeing any more questions. It's 5 to 12. So again, on behalf of the Ontario Municipal Fire Prevention Officers Association, I do want to thank you for taking time out of your day to present. Definitely, you gave us a lot of information. You know, and you know, if I get an opportunity, I'll let the membership know if we approve the submission coming to Oakville.
Yeah, I think it's just to speak to that. I mean, part of why I wanted to speak today is that I do think we have to have some conversations around this and introduce the concept and let people become aware of and familiar with how it works, because knowing and sharing this information in advance of, say, having a BMEC or a US standard, this is the only way we're going to be able to communicate about it. And I think, in fairness, all your questions have to be answered to satisfy how it's going to work and how it works. And I've explained this. I've worked with Wagner on almost all of these projects. They've already gone down this path doing the same thing in Europe. And I did lean on that quite heavily, saying the expectations for fire protection in Europe and Britain are quite similar to what we expect here. So if we have to have some confidence that what they're doing there is that we can also lean on that, and we will start to adopt it and bring it over. So it's innovative. I think there's situations, it's not going to replace sprinklers everywhere. There's places where it's not going to be effective or efficient, or we may not even be able to get to a threshold that works for the commodities. But like the water mist and the gas and even some of the compressed air foam, in certain situations, I think it's as good or better than sprinklers.
Yeah, I mean, I'll be honest, when I first heard about removing sprinklers from a building, my first reaction was, hell no. So now Wagner, they're not the only manufacturer though either.
No, they're not. They're not. You're quite right. And I meant to look up some of the other ones because the New Brunswick project was leaning towards a different manufacturer, and I can't remember the name of that. The first one that comes up in a Google search is FirePass, thanks to their advertising. I can't remember if that's a full, if they're trying, I think it's presented as a keeping the hypoxic environment versus a deluge style dump of bringing it down. No, Wagner's not the only game in town, but they are going to be kind of that brand name, your Kleenex of these systems, because they are the early innovator and implementer of it. So
yeah, so I guess depending on the manufacturer, they may have their own maintenance requirements and so on. So
yeah,
it won't be a cookie cutter approach.
Not really. I think in those cases, I'd be looking at their control system in particular, because the back end, the nitrogen generation, it's being used in all sorts of industries. Like generating nitrogen isn't like a unique or fire only type of application. So nitrogen generation, there's multiple ways of doing the nitrogen generation. So you're really looking at the reliability and the capacity. And then the oxygen sensors, again, they're used in lots of industrial applications. I think you just want to say, is it right for the environment? Like the ones in the warehouses, you have to make sure they're at the right temperatures. So I think really what we're getting down to is the controls and the thresholds, and being able to manage that and ensuring that we've got the right ignition threshold when we come into this.
Now, these systems, would they be on average cheaper to install than a sprinkler system?
I haven't had a straight answer from anybody on that. As they get larger, I think the systems are cheaper to install. There's very little, I mean, there's very little materials. You're not putting in anywhere near the amount of pipe or that. But I think you have to factor in operational costs because it's an always on system. So I honestly don't know where you stand at per square foot. I've tried to get some information on that. A lot of the people looking at installing this, that to them isn't always the driving factor, is the cost. For them, insurance companies are lowering premiums because of the better protection of the goods in the sense of the environment, and less potential for having to discard the full warehouse. So the insurers are on board with underwriting these systems, and because of that, I think that's why a lot of owners are switching that way. The systems, like Dr. Oker was familiar with it. They brought it to Canada. We're looking at another one. We're hoping to bring one into the Guelph area, just as a heads up if anyone's from Guelph is still on the call. But we're hoping to start talking about that in the Guelph area. And it's, again, a European company that's familiar with it. And they just said, we want this system. So they're kind of dragging it with them as they come to North America.
Fair enough. All right.
Which insurance company? Oh, I don't know which ones.
Yeah. Well, I do again want to thank Steve and Leslie for taking time out this morning to present some very good information here. For the participants, thank you for attending also. Just wanted to give everyone a heads up that our next training session will be on April 14th at 9:30. And we're going to be looking at assessment, testing, and maintenance of smoke control equipment in high buildings. So hopefully a lot of people can make it to that one too. And I guess on that point, this is where we say goodbye and take care, everyone.
Thanks, everybody.
Thank you, Leslie.